Good day, everyone. Today I'd like to talk to you a bit about pressure gradients, and are they a myth or are they reality? And I'll infuse that a little bit with some examples that relate to an area that I've really worked on for a long time, which is real-time monitoring and control, and a little bit of philosophical musings on the side. So my name is Hani Elshahawi. I'm just retired from Shell. Previously worked also for Schlumberger, a former SPWLA president, and was distinguished lecturer 2010, 2013, and again in 2018. So this work is based on kind of fusion from the 2010 era with a little bit of additions from the other works. So first I'll start by saying that the future is here, and it's just got a lot nearer over the last few months after COVID. You know, all the trends that were ongoing with respect to digitalization of everything have just accelerated a whole bunch. So we've just maybe taken 2 years worth or more of digital transformation and compressed it in 3 to 4 months. So the question is, you know, what are we doing about that? How are you changing the ways we work? And hopefully this will be a recurrent theme and you know, subject for future webinars. But in this particular one, I want to focus on another area where I've spent a good part of my career, more than 15 years actually, working on and still continue to be active in, which is formation testing and sampling. So first, I'll take you to the other corollary area that I want to talk about, which is real-time monitoring and control. Here's a picture of one of the robotic geologists, one of the Mars rovers. There was several of them, and the latest one is about to launch actually next year. And essentially, it's a roboticized geologist, and it collects rocks, does the analysis on them using LIBS Raman and other sophisticated analyses, and it beams it all to Earth in real time. There's no little geologist hiding in any one of those rovers. So we've been doing that for years. This is not really new for the good part of the last 15 years. Remote control surgery also became a reality roughly around the same time that I published the original work on this, which is 10 years ago. And right now, you know, the equipment that you see here is commercial. It's very expensive, so that, you know, a lot of companies have been working on sort of downsizing it and streamlining it, making it more affordable. But it's a thing. You can actually operate today on a, you know, open heart surgery halfway across the world. That is actually doable using such equipment. So real-time monitoring and control is a central tenet of this concept. And we can apply it and have been applying it in the oil industry as well, particularly in formation testing and sampling. Conceptually, it's very simple. It's about connecting the well site and its operations to the various parties and parallelizing the work and collaborating around real time. And then the requirements really for that are quite simple: secure web link, you know, minimal delay, but importantly, the bidirectional capability, because it needs to be both the monitoring of the data and sending of the commands or the controls to direct the operation. The benefits are plentiful. They include travel logistics savings, especially in the current environment. That's very obvious. HSE personnel security, once again. Collaboration, knowledge transfer. That's a big deal, because in a lot of our workflows, we have these silos which are created by disciplinary boundaries, by geographic boundaries, or what have you. And parallelizing the work through real-time collaboration, it diffuses those and dilutes those boundaries. By the way, this is a big tenet of digitalization. You hear a lot about digital transformation. The core of digital transformation, in fact, is the removal of silos. And the other core part of digital transformation is making decisions when it counts, meaning that you can take the data, but you actually transition that not just to insights, but actually decisions, actions. And those actions also now change the outcome of your business process. So we've used that a lot, information testing. Some of the applications of information testing, just very briefly, because I don't want to go into a lot of detail about that, include pressures. And of course, once you gather formation pressures, then you can plot gradients and establish contacts, fluid contacts based on those. Sampling of reservoir fluid sampling, and downhole fluid analysis, which is used both as a complement to fluid sampling, but also as an answer product in itself, because it will allow you to look for intricate changes within the fluid composition, either laterally or vertically through a well. You can also get permeability related data, which you can then translate into deliverability, as well as conduct in situ stress testing using information testers. Now let's focus on gradient analysis, which is kind of really the core topic of my talk here. The classic way of doing gradient analysis relies on Pascal's law, which essentially implies that if you move away from transition zones, kind of your contact area, the continuous fluid phase pressure profile, the dominant phase pressure, whether it's oil or gas or brine, is given by this formula, dP by dZ, mostly driven by gravitational forces, equals the density times the gravitational constant, which is the acceleration of gravity here. Now, there's a lot of assumptions implied in this, although this is very commonly used as if it's ground truth. One of those assumptions is that you have a static reservoir under virgin conditions, which that is commonly understood. So, if you have, for example, a depleted reservoir due to production, then, people are a bit more cautious using just gradients. And that you have a single fluid column that's away from the transition zones, that's implicit here already, and it's uninterrupted by barriers or fluid infusion. Okay, and importantly, that you have the absence of wettability or supercharging effects. Some of those effects are documented and some of the works are cited here. So these are all assumptions, okay? But, given those assumptions and given the caveats, if you take the data then and you plot it as is shown here, you have n number of points, you have the corresponding pressure data and the depth pairs for each one of those points. So you can draw a line, and basically it has, the classic linear formula, y equals mx plus b. And in this case, you can translate that into the equivalence of pressure and subsea vertical depth. You need to have, vertical depth here or relative depth. You can compute then variance from the mean y, and covariance of xy, or any one of these. And then, of course, you can compute the intercept and the slope. Other things you can calculate using basic linear regression is your correlation coefficient, standard deviation of the slope, the standard error for your y estimate, which is will be your depth or your pressure, and the standard deviation of your y and x predictions. Okay, so this is basic statistics analysis. Now, this is some real data here collected from a number of gauges. Notice that the gauges are separated slightly, some of them. That's due to slightly different accuracy on those gauges. So it's not separated for display purposes, but rather that's just, some of them are strain gauges, some of them are high resolution and accuracy quartz gauges. And you see some of them cluster on top of each other, so you can get some really, really good results by doing that. This is a particularly, homogeneous, permeable sand reservoir. You can see that from the permeability curves here, the NMR permeability curves. You can see that from the density neutron. You can see that, how the mobilities, kind of plot on the higher end tends to a couple of hundred millidarcy. And then when you plot those, you get really, really good lines, if you look at the slope of some of those lines, 0.271 psi per foot. Another one, which is a completely different set of data, is 0.27, 0.272. I mean, this is amazing, right? So what's the problem here? Is that it? Do we, is it all about gathering a whole bunch of data and plotting it and getting your statistics right? No, it's a bit more complex than that, because if you presume that there's a linear dependency of P on Z, P being the pressure and Z being the depth, it means that you're already predisposed or biased towards interpreting intervals as being connected. So you've already presupposed that. And it means also that subtle changes may be obscured by your standard regression analysis. So what if you have something in between? So if I go back to my previous example, there was, a little carbonate stringer in there. What happens with that? Is that a barrier to flow? Do I lump the points on either side of that, or do I construct it separately? We'll see some of those as they come up in the examples. More importantly, there's other things we have learned over the years now. We now understand, for example, that all hydrocarbon columns are graded by definition, meaning that just like an orange juice or some other heavy juice, mango juice or something else, would settle if you left it for a while in your glass cup due to the gravity. The same thing happens actually to hydrocarbons, because hydrocarbons are complex mixtures. They're not actually a singular fluid. And so they're affected too by gravity, which means they separate and segregate by the gravity. So all hydrocarbons actually are graded to some extent by definition, some more than others, which means that by definition, you don't actually have a line that can define the density, because the density is actually varying through it. So we know that. So how come actually then we're constructing lines? It's almost a paradox here. And then we know also that reservoir compartmentalization is quite prevalent. It's not rare. I wouldn't say it's the exception rather than the rule, but it is quite common. And that pressure is a necessary but insufficient condition to establish connectivity. In other words, if you have pressure continuity, that will be a requirement for you to know that you have a connected column up and down. But just having it doesn't prove that it is connected. You need other things. And just to show you that reservoir compartmentalization is quite common, in this study by Deep Star about 10 years ago, they looked at 28 Deepwater Gulf of Mexico fields. And they plotted kind of, where do they perform relative to what had been pre-diagnosed. 75 of these reservoirs underperformed, both on rate and recovery. And the number one cause of that has been compartmentalization. So it's really quite prevalent. The other thing which is prevalent, as I mentioned, is complexity. So we do know that we have graded columns that look like this. In this series of bottles, you can actually see the coloration change up and down the column. We know that reservoir architecture, particularly in larger, deeper reservoirs, can be quite complex. And we know that in columns, thick columns, you can have this large viscosity gradients, sometimes going all the way to tar mats at the base of those columns. So now that we know that, what does that mean with respect to our approach to the data? Should we treat it any differently, or should it just be a statistical exercise? So to get at the root of the answer for this, I think we need to examine kind of conceptual frameworks by which we think, particularly in the Western world. To some extent, these have parallels also in the Eastern philosophy. But there are two dominant conceptual frameworks that have shaped the scientific methodology over the years. One is deductive thinking, And it manifests itself in how you would use statistical means, for example. And this was first taught by Aristotle. He taught basically that the whole is equal to the sum of the parts, and that reality is discerned only by the sensible, by what the eye can see, the hand could touch, and such. And it uses past information to predict the future state. So this is a paradigm. And it's pretty much at the heart of what we do with things like statistical analyses, because it treats the data as the truth and the only truth. On the other hand, Plato, who's Aristotle's teacher, of course, his teachings were at the root of the inductive thinking method. And that's, we use that quite a bit in petrophysics with pattern recognition, for example. Now, he taught that the whole of reality is greater than the sum of its tangible parts, and that one must use past information to construct patterns that are not only based on the input data, but also on the logical consequences of those data. So think about that a little bit, and the parallels between that and what we talked about with respect to compartmentalization and grading. Those are things we know exist, yet we may not see them in the samples of data that we collect. So how can we invoke that in our analysis? Now, I offer here, which I have essentially been using in much of my work, whether it's related to digital, whether you're related to formation testing or otherwise, an alternative which is called abduction reasoning, which is really a better way. And you can apply this, by the way, to business thesis, to exploration thesis, to data analysis and analytics, whatever. But abduction reasoning is kind of this different creative process in which you pose a generalization and it's precipitated initially as an explanation of your observed facts. So that means you plot, for example, the linear trend to your data. However, you continue to interrogate and refine and revise as you collect more data. So you take that explanation and you put it to the test against evidence that can then refute or confirm it. And then, you know, that hypothesis will either persist or has to be changed. Now, the stability of your interpretation is reached upon what's called saturation, which is when collecting new data or analyzing different aspects of the evidence do not lead to any substantial or further insights. So you start essentially with abduction, you formulate the hypothesis, you go to deduction, and you look at the logical consequences of that, and then you go to induction, which means you experimentally test those consequences. By the way, as I mentioned, this is very relevant to doing scientific experimentation or even business experimentation. So when people talk a lot about doing your proof of concept or looking at the minimum viable product, this is the same process actually that you would have to invoke. Okay? Now, how does that apply to formation pressures? Well, it means that the details of the acquisition, of the analysis, and everything else matters. So how you got to the data and what the logical consequences of those data and how they were collected matter just as much as the data themselves. So for example, a single downward pass during acquisition is really the only viable way to collect reliable gradient quality pressure data that you can then hang your hat on the interpretation of. Why is that? Is because there is a thermal hysteresis effect that affects just about all gauges because of the means that are calibrated. It also is physically easier for the tools to heat up because of their mass than it is for them to cool down, which means that effect of temperature displays a lot of hysteresis effects. And so it matters a lot how you collected the data and in what order. So for example, filling in data between a whole bunch of data actually doesn't really work. Statistically, it doesn't work. Also means you have an adequate number of data because, well, guess what? The statistical precision, but also your ability to interrogate your hypotheses is quite dependent on how many tests you have performed to that hypothesis, as per the previous slide. So the right number of data and oversampling is sometimes actually the right way to go. Again, that's the kind of insight you can bring into your experimentation. identification of capillary pressure, supercharging, and all these effects. And then, importantly, real-time monitoring and control, which, as I mentioned before, will be maybe subject for another webinar because it deserves one by itself. But it's a framework that allows us to do that experimentation on the fly, as opposed to after the fact, because you can't really conduct the experiment after the fact. You can't go back and collect more data after the fact. You have to do it right there and then. For multi-well data, there's other nuances that one has to factor in, which is the need to cater for the complex interplay between pressure, depth, and fitting errors, because there's a lot of errors that compound here. And then you need to draw these ellipses of uncertainty and see what they mean. So I refer you to this really seminal work by Collins et al. In 2007 for more on that. I'm going to focus here in my examples on single well. Here's a gradient interpretation methodology for a single well. So you start by quality control, discriminating the poor data from physical trends. And then as you're doing that, you ensure that you're collecting sufficient pressure samples and downhole fluid analysis data. We'll come to the significance of sample and downhole fluid analysis data a little bit later in the examples. But they are important because they're corroborating independent evidence. Because as I mentioned before, pressure is a necessary but insufficient condition to establish things like connectivity. You can establish the lack of connectivity, but not the connectivity. So you can prove basically the guiltiness, but not the innocence. And then you pick zones using petrophysics, geology, and what's called excess pressure, which I'm going to show in a little bit here. And so this is how you bring the contextual information into the picture. Okay, so I'm a big advocate, for example, of conducting analyses using pressure data with the logs alongside of it. Obviously, being a petrophysicist, I have a bias for that, but really that's the context that is absolutely necessary. And then you fit the models to the pressure data and you test appropriateness, and then you compute local density and with error bounds, you compare those to other corroborating data like in situ or sample density, and you iterate. You compute the positions and uncertainty of the contacts, and you go back and revisit your hypothesis if it doesn't work. A simple tool that everyone can use here, highly valuable and easy to do, is the idea of residual excess pressure analysis. And it's really nothing more than a transformation of the data so that you can augment and zoom in on the trends, because the trends matter as much as the overall fit. So first, you start by performing gradient uncertainty analysis on P versus Z regression, assuming that everything is connected. So you make that assumption knowing that it's wrong. And then you use the regression equation from that to calculate the pressure gradient for each data, and then you subtract the two. You calculate the residual pressure by subtracting the measured minus it from it the gradient or the fitted one, and that produces your residual. And then you plot that residual versus depth in the same way you would plot the actual pressure data, and what that does then is it accentuates the trends. Okay, and then you can do that for every sub-interval that you've identified. So now if you see breaks, you go back and say, oh, I need to break down these intervals into smaller ones. I cannot really be lumping them. So here's a synthetic example, just used to illustrate. So look at these two sands. We fix the depth here and we vary the pressures. Okay, so each one will have 5 tests separated 5 feet apart for simplicity. So I'm going to show you very quickly 5 models. Model 1 is a constant oil density, what it would look like. Model 2 will have lighter oil density and denser below, which is what you would generally expect if you have, some kind of grading, and these two are connected. Denser oil above and lighter below, which would tell you right away that they're not vertically connected, because if they were, it's really not possible to have the denser fluid sitting above the lighter one. And then model 4, the same density, but you have an offset of a PSI, and then vice versa for model 5. So I'm just going to go through these real quick here. So this is what the residual plot will look like if you had the same oil throughout. Of course, if you look at the statistics here, well, you have, R squared of 1, and, obviously, you have a very tight uncertainty bound. Now, if I had lighter on top, it fits very well on a line. It'll have an R squared of 0.999, but that's exactly the problem. It obscures the actual complexity in the column, because the reality is the top fluid is denser than the one, is lighter than the one below. And so actually, if you plot the residuals, then this is what you get. You get something sloping this way, followed by that one sloping this other way. And that tells you that, hey, you need to go back and actually subdivide those two, because they're not lying on the same trend. You wouldn't be able to tell that if you just plotted it like you would on the left here. This is the same thing, but now heavier on top, which, as I mentioned earlier, again, 0.999. So looks no different than the previous result. You'd be happy with it, but actually it's obscuring a very important finding here, which is that you probably have a boundary between those two. That shale barrier that I showed earlier is actually probably a laterally contiguous shale or regional seal. Here's what happens if you have a 1 psi pressure step, and if you have another psi minus to the minus side pressure step. So this is how we would do it with real data. You know, you would plot it like that. You would look for the outliers. And by the way, the two lines here, and you can read more about that in this SPWLA paper again. The two lines here, one is actually sort of the is honoring the actual data, and the other one is modeled based on your expectation of pressure repeatability and depth uncertainty. And in reality, these two should converge. So the fact that you have two outliers here tells you that these two were probably collected out of sequence or something else. But that detail will all be there in the raw data, which is why raw data is really important for when you're analyzing pressures. It's a little bit like sushi, I always say. The more raw, the better. The more cooked, the less tasty or less palpable it is. So you exclude these, and then you perform it again. You perform your regression again, and then now you can see a convergence, a better convergence of your expected and modeled envelopes. Here's an example that I'd like to share with you. It's a simple example because it's, as all of you petrophysicists on the line will recognize, is water bearing, and you don't often get many examples of nice clean sands with water in them, So these are the pressures that were collected right here. So when you glance at this one, so what is this? Looks like water, maybe, really, likely. But what is this change between the baseline resistivity here and over here? They look equally clean. Density neutron doesn't look a whole lot different. There's a little bit more separation, but not a whole lot. So is this different salinity perhaps? Or is it different net to gross? Maybe, that's a possibility. Do we have an issue of vertical connectivity perhaps? Is this a sealing shale? It's pretty thick, so it might be, could likely be. So should I be fitting a straight line to these just because I can? And here's the exercise of doing that. If you fit a line to it, well, it gives you 0.995, I think, correlation coefficient. So it's pretty darn good. But again, in light of what we talked about, should I be doing that or should I be doing this? So that's really the question. Well, here's what you would do. If you put the confidence interval, you'll find that actually the bottom one lies on the outside of your confidence interval, which means statistically speaking, these two, you cannot say that they aren't connected. 95% confidence limit includes this. Well, but when you use now your excess pressure analysis, now it tells you a different story. And why is that? Is because now your excess pressure tells you that those densities just are not the same. The slope is not the same. And that is similar to model 5, which I showed earlier. All right. Now, what actually happens here, because we did take a sample, and that's the benefit of actually being able to sample, is the reality is the salinity of this sand up here, the water sand in the sand, is significantly different than the one below. It's about 100,000 ppm, and the one below is about 180,000 ppm. And you can reconcile that by looking at the different resistivity calculations. You can back calculate your resistivity if you had 130, or if you had 180, or if you have 100, and so you can see where it matches up here. So the high net to gross sand intervals are really comparable. Both of them are high net to gross, so that's not the issue. The issue is they have different salinities, which is why you're different resistivity baseline. But you could deduce that from your pressures, but only if you use the insights of your residual pressure plot, as well as accept that it's a prevalent thing that columns like this are not connected, even though they would fall on a line. So just because things fall on a line doesn't mean that they're necessarily interrelated. And by the way, this is a much bigger issue that we can discuss in future webinars. But it gets to the heart that it is not just about the data. It is not just about your subsampling of a complex system. Like if you took a bunch of rocks, for example, rock samples, that does not constitute the totality of your reservoir. That only allows you to fill in some inferences about the totality of your overall model. And the same thing is here. So one always has to approach pressures with that. What about oils now? Well, it gets even more interesting, okay? Because with oils, you also get gravity diffusion, which gives you compositional gradients. So for example, the Gibbs sedimentation equation, if you simplify, will give you basically grading with the different molecular weight components, and there's hundreds of these components in any given black oil with depth. So both molecular diffusion as well as thermal diffusion, as well as other non-equilibrium forces that you may have, like convection, ongoing charge, biodegradation, leaky seals, water washing, all of these can cause even more complexity, not just the gravitational component. So that together means that with oils, you really, really have to be careful about drawing a line. And this is our second example, which talks about that. And you can read more about that one in this SPE reference here. Once again, bunch of paper on an Excel plot without any logs to go with it. Sure, I can draw a line through them. Very good correlation coefficient. End of story. So everything is connected, right? Well, if you have retained anything from what I just talked about earlier, is maybe not. Why not? Well, look at those pressures. They're gathered in this sand body here, in these stringer sands, and in this massive sand below. Why did I presume that all of these are connected a priori? Should I presume that they're connected a priori? Just because I have a whole bunch of data with a little bit of scatter on them doesn't mean that they are. Again, and even if they were, that still doesn't mean that this is connected in production space. Now let's look at the detail here. And this is where sampling and other corroborating data really comes in to make a big difference. So I'm going to show you here the results of the so-called downhole fluid analysis measurements that were collected in this part of the sand, this one, and you see the 5 stations here at the top of it, in the middle of it, and at the base of it. Because why are we doing so many? Well, because we want to understand the grading here, and we want to understand, is this similar to this or similar to that? This is a rough breakdown of the composition. C1 is basically your methane, and it's expressed in gram per cc, which you can add up these gram per cc. So this is the partial densities of the various components or group of components. And then if you add them up, more or less, it gives you the density of the fluid itself. Okay, so C2 to C5 is 0.03 and so on. So what you notice here is when we collect based on this data that we collected in those two top stations, they look very similar. So there's not much upgrading happening here. But when we go below, the methane fraction increases, and the C2 to C5, which is the other part of the gas, increases, and then the C6 plus fraction, which is essentially liquid, decreases. What that really means is this is a lighter fluid. Hey, a lighter fluid sitting below a denser fluid, how's that going to work? If this was a continuous column, that wouldn't work. So by itself, this is already a warning sign or a flag that, hey, we cannot connect these pressures. Definitely not, because this is independent of them. And then as you go down the column, you see that it's increasing with density, increasing with depth. So the density is increasing with depth, which is what you would expect for a thick compositionally graded column. So this is normal. So I can say that these are connected, but it's still not a line. It's actually a curve. But this is not connected to that, which is not connected to that. And if you compare then the new gradients that you draw with those insights in mind, so here you get 0.67, 0.67, 0.62, which is a lower density, just like we said here, based on that data, 0.65 and then 0.67. But of course, if you connect the bottom to the top, they all line up very nice. But what happens in the middle? And with any statistical analysis, the endpoints dominate everything else. So your extremities will always dominate your linear regression. So be really careful about that. The reality is, actually, we have a vertical barrier. This is very significant, by the way. In that particular example, this is a regional multi-flooding service, which is, you can chase for miles away from your well location. And it means also that your reservoir seal pairs here are independent, which means even if you, for example, had a leakage in one or a incomplete fill in the other, it doesn't mean it's a detriment to the other reservoir seal pair. So you can, you have independent prospects to go after. That's a big deal from an exploratory standpoint. What I'm showing here at the last column is the lab data, the lab analysis data, 0.66, 0.66, 0.63, 64, 0.66. Not only does it show the exact same trends, which is an independent corroboration of this interpretation. So remember, the paradigm that I invoked, or the framework, is that you bring in other data and you continually test your hypotheses until you don't get any greater learnings. So this is an application of that. Impressively, the accuracy between all these different measurements, physically different measurements, is within 0.01 gram per cc, which, by the way, is as good as you're going to get in any high accuracy lab grade analytical tool for density. 0.01 gram per cc from an accuracy point of view is very impressive. But this is real data. Now, we can integrate other things too. So, for example, in the workflows that I've done quite a bit of work on with my colleagues at Shell, we were integrating advanced mud gas logs. So, for example, from advanced mud gas logs, you can get the C1, the methane relative concentration, and you can get also your methane isotope analysis, shown here in the red dots. These are point measurements. So if you plot them here, though, and you plot the GOR measured from the fluids or measured using downhole fluid analysis tools, you can actually see the parallels. You see that F and G, which are the two top stations, are very, very similar. Of course, that's also corroborated by the very similar density. You can see the flat lining in both the methane relative concentration as well as the thermogenic charged content given by the methane isotope analysis. And then if you go down here, though, you see this big jump in GOR, and you see the same trend actually in your methane concentration in the mud gas, and you see again that inversion in your methane isotope analysis. So it all hangs together. So as I introduce more data and revisit and test and try to fail my hypotheses, it's holding. Okay, so now I reach that point of saturation, which is how I was referring to earlier. And this, I think, is the better way of doing scientific work, especially discovery type of work. Whether you're exploring for oil and gas or whether you're exploring for technologies, this is the better alternative. In conclusion, then, hope I convinced you that grading and compartments are prevalent. You can, visit some of my other works in the last 10 years, which talks about some of those. Linear gradients are the exception, not the rule, mainly because most of the fluids we look at of interest, particularly hydrocarbons, that is generally not the case. We can approximate by a series of lines, but it's not a line. So you have to give it careful thought and quality control before statistical analysis. Before, not after, before. And while you're doing it, but not after the fact. Consider pressure, depth, and fitting errors. It's very important to keep the context in mind. The contextual information is as important as the data itself, if not more important. So integrate with all the available data. You plot the pressures alongside the logs as a minimum, and use the excess pressure plot to accentuate the trends, because trends are an important proxy for context. Extrapolate only if flow continuity is proven beyond doubt by independent corroborating data. So you don't draw the line across just because you can, but because there is evidence to suggest that you might or should. And lastly, I keep you with the thought that real-time monitoring and control is not really a luxury, especially not in today's environment, but it's a must. And hopefully in the future we can talk a bit more about real-time monitoring and control, because I think it's very topical. So I'll leave you with this slide, maybe as a bit of a teaser for the next webinar. So real-time monitoring and control, information testing applications, and really beyond that is about intervention, it's about decision-making, and very importantly, it's about integration and collaboration. And the beauty is you can do that anywhere, anytime. And that is not any more relevant than in today's environment. So thank you very much for your attention, and look forward to engaging with you in future webinars.